Take a look at these three polygons right here. I listed the areas of each. This has area 2. This has area 1, 2, 3, 4, and then this is half of 2, which gives us 5. And then the diagonals of this square are all square root 5, so this has area 5 as well. I've also listed the number of interior lattice points, 2 here, 4 here, and 0 here. That's listed there. And also the number of boundary points of each, which we get 6, 8, and 4. Now, if we look at this table of values, I wonder, is there a relationship between the columns? Is there a relationship between the area, the number of interior lattice points, and the number of boundary lattice points in a polygon in the plane whose vertices are at lattice points? It turns out that there is, and that's the content of what's called Pix Theorem, and that's the center of today's video. We're going to develop a proof of Pix Theorem, and there are many proofs of this, but we're going to develop a proof that's actually longer than the usual ones. And the reason is because this process of proving this mimics something that happens a lot in mathematical research, where we actually look at data to infer a possible relationship, start with small examples we can control, and build up to get a unified theory. So the first thing we want to do is actually see what a relationship could possibly be. Now, in the three examples that we have here, we notice that all of the number of boundary points happen to be even. And if we have data that we're collecting to try to infer a theorem and we see a bunch of even numbers, it'd be good to divide by 2, because that might be more indicative of the raw nature of the data. So if we divide by 2, we get 3 here, we get 4 here, we get 2 here. And then we start to see something. If we look at these two numbers here and compare with this, we actually get that the sum of these two is 1 more than this thing. So it seems like in general, the area is the number of interior points plus half the number of boundary points, these two, and then minus 1. And it turns out that this actually is the case in general. And this is known as Pix Theorem. And we're going to prove Pix Theorem today. So proving this in general for general polygons, and this actually works regardless of what the polygons look like. They can look like this and fold in on themselves. They don't have to be convex polygons as long as they have straight lines and their vertices are at lattice points. Okay, so proving this for a general object like that seems quite complicated. What we're going to do then is take the strategy that I usually take when I'm doing mathematical research, which is start with basic building blocks and build up as you go along. So to start, what we'll do is look at maybe one of the simpler shapes, which is rectangles whose sides are parallel with the coordinate axes. So let's look at that example, that particular case, and try to prove Pix Theorem there. All right, so say we have a lattice rectangle. So our vertices are at lattice points. And let's say the rectangle has length n and width m. All right, so let's actually count each of the different pieces. Let's write down the theorem that we want to prove here actually, that in any lattice polygon, the area is the number of interior points plus half the number of boundary points minus 1. All right, so let's take a look. So first of all, the area, because it has dimensions mn, is m times n. Okay, so now what about the number of interior and boundary points? Let's count the boundary points. So we have n boundary points right over here, and n over here as well. Or do we? The length of this thing is n. So for example, if it had length 3, we'd have 3 length 1 line segments, which actually gives us 4 boundary points there. So actually, the number of boundary points in the rectangle is m plus 1. Okay, and then similarly, here we'll have m plus 1 boundary points, and then here we'll have m plus 1 boundary points as well. So the number of boundary points is the sum of these 4 numbers, which is twice n plus 1 plus twice m plus 1. All right, but we need to subtract these double counts that we have at the 4 corners. There's 4 of them, so we subtract 4. Now if you expand this, you see that we have twice n plus 2, twice m plus 2, so we get a factor of 2 as a constant, which cancels with this negative 4. So this works out to twice n plus m. All right, so b over 2, which is the quantity we actually want, is n plus m. Okay, great. So now the question is, what's the number of interior points? So we can think about the interior points as everything that's inside of here. Right? This entire thing is an array of n plus 1 times m plus 1 many points. Now, if we go into the interior square, we're reducing n plus 1 to n minus 1 and m plus 1 to m minus 1. And we get an array of n minus 1 by m minus 1 many points. So the number of interior points is n minus 1 times m minus 1. Okay, and if we expand this, this works out to mn minus m minus n plus 1. So let's check that this actually works. We take the number of interior points, that's this. We're going to add n plus m, that gets rid of this contribution. And then we're going to subtract 1, which gets rid of this contribution. So we do actually get the area. So great. Pix theorem works for rectangles. All right, so where do we go from here? We have Pix theorem for rectangles. What's a natural next step? Well, the way we're going to think about this and where we're going to move on in general is once we have one shape, we can think about decomposing that shape into other shapes and using the fact that we know Pix theorem for this shape to figure out Pix theorem for the other shapes. For example, if you take a rectangle, you can decompose it into two right-angled triangles, right? And because of the way these triangles are drawn, the number of boundary and interior points are going to be the same, right? Because these triangles are actually congruent, and their orientation has their sides parallel to the axes. Now that we have Pix theorem for rectangles, what we can do is think about taking a rectangle and decomposing it, and then using Pix theorem for the rectangle together with the decomposition to get Pix theorem for other shapes. For example, we could cut this with this diagonal and get two right-angled triangles. And as a consequence, because these two right-angled triangles are actually congruent and their sides have the same orientation with respect to the axes, the number of boundary points and interior points in both of these are going to be the same. So we can use that together with the information that we have for the rectangle to prove Pix theorem for right-angled triangles. So let's go ahead and actually do that. Okay, so I've taken a rectangle here. Let's call the rectangle R, right? And this area, interior points, and boundary points will be written with the subscript R involved. So we know by Pix theorem for rectangles that the area of the rectangle is the number of interior points in the rectangle plus half the number of boundary points in the rectangle minus 1. All right, so let's call this triangle T, and then look at relationships between the different statistics for T and the statistics for R. So first of all, we have that the area of R is twice the area of T, right? Now, it would be beneficial to write this in terms of R itself because we have the formula for R. So we'll rewrite this as the area of T is 1/2 the area of R. Okay, so let's do a similar thing with the number of boundary points and the number of interior points in T itself. So let's look at the boundary points of T. So T looks like this. We can partially relate the number of interior points or the number of boundary points in T to the number of boundary points in the rectangle. But then there's this interesting weird part, which is the diagonal. And unfortunately, the diagonal could be at any slope, and we don't really know what that slope is. So what we'll do is, since we don't know really what's going on, I'm going to take all of these points right over here and say that the number of them is some fixed number that I'm going to call x. I don't know how many points those are, but I'm just going to call them x. We know that they are involved somehow in the number of boundary points of the triangle T. And we also know that they're involved in the number of interior points of the rectangle R. So that'll come to benefit. Okay, so now let's analyze what's happening with the interior points of T. So the interior points of T is everything inside of here. right? But we have two copies of T going on. And we can see that the number of interior points in T, we have all the interior points in T here, a copy of those, and they almost form all the interior points of R, except for this strand of X points, which aren't involved in the interior of T as well. So the interior of T, the number of points there, plus the number of points in the interior, plus this X, is the number of interior points in R. Okay, so we can write then that the number of, I'll write that as an equation in terms of R actually. So, or maybe we'll go back and write this in terms of R instead. So AR is twice AT. And then we also have now that the number of interior points of R is the number of interior points of T twice, plus this contribution that we don't necessarily know called X. Okay, so now let's look at the number of boundary points of T. So the boundary points of R, a lot of them are involved in the boundary points of T. We see that if we look at the boundary points of T from this lower triangle, we get boundary points of R together with these X values here. And then in this copy of T, we have the boundary points of R and this copy of X as well. In total, with these two copies, we will have covered every single boundary point of R, except we'll have covered these 2 points twice. So if we took the number of boundary points of T from this contribution and added the number of boundary points in T from this contribution, we need to subtract 2, and then also subtract the 2 times we go over this strand of points right over here to get the number of boundary points in R. Okay, so if we rearrange this and divide by 2, we get that BR is, because we have 2 copies of BT here, we get BR over 2 is B sub T minus 1 minus X. So let's piece all of this together and see what we come up with. So the information we're given is that we know from earlier that Pix theorem holds for rectangles. So the relationship we get then is that 2 times the number of interior points of T plus X plus this quantity over here, BT minus 1 minus X, minus 1 has to equal the area of R, which is twice AT. Okay, so let's look at what this looks like overall. These 2 contributions here cancel each other out, and we're left with twice IT plus BT minus 2 is twice AT. And now if we divide this quantity here by 2, we get AT, we have a negative 1, BT over 2, and IT, which is exactly what we want for Pix theorem. Great. So using this cool idea, we're able to establish Pix theorem for right angle triangles. I wonder, can we get Pix theorem for a general triangle now? Our idea with a right triangle was to look at it as a decomposition of a rectangle. So can we think of using rectangles and right triangles to somehow decompose them and get an arbitrary triangle like this? Well, there is a cool way. One way you can do this is by boxing this thing inside of a rectangle whose sides are parallel to the coordinate axes. Now you see that this inner triangle sits inside of a rectangle and has these other right angle triangles that with it form the big rectangle. So our idea then could be to use Pix theorem on the rectangle together with these 3 copies of right angle triangles. They might look different, that's okay, to figure out Pix theorem for this arbitrary rectangle here. So let's go ahead and try and do that and see what happens. Okay, so we've taken a general triangle and decomposed it into a rectangle R and 3 right angle triangles T1, T2, and T3. And we know the rectangle and the 3 right angle triangles all satisfy Pix theorem, which is written right over here. So what we want to do is figure out the same relationship for this arbitrary triangle. So to do that, we'll relate the boundary points, area, and interior points of the small triangle to these three triangles and the big rectangle. So the first thing we can notice is that the area is summative. The area of the rectangle is the sum of the areas of all these triangles. So write that as AT1 plus AT2 plus AT3 minus AT. Okay, now let's look at the boundary points. So the boundary points of R are the points that are all over here, right? And so they cover parts of T1, T2, and T3, but not all of them. If you want to include T1, T2, and T3, you have to include this line segment, and this line segment, which actually covers exactly the boundary points of T. So the boundary points of R plus the boundary points of T is the boundary points of T1 plus that of T2 plus that of T3. If we were to rearrange, we'd get then that the sum of the boundary points of the three right-angled triangles is this quantity, the boundary points of R plus the boundary points of T, so we'd have to subtract it if we want to put it on this side. To double check that we don't have any double counting here, you'd get this vertex, and this vertex counted. This vertex and this vertex would be counted in T3. This vertex and this vertex would be counted for T1. And then in here, we'd get these two counted for T2, which balances out when we count R. The boundary points of R would count each of these vertices exactly once. And then the boundary points of T have these as vertices, so we count each of these once. So we should be okay in this expression that we have here. So finally, we need to know the interior points of the rectangle. So the interior points of the rectangle are all filled in here, and parts of them sit inside of each of these right-angled triangles. So we get the interior points of T1, the interior points of T2, and the interior points of T3. And then we also get the interior points of T, but now that doesn't cover everything because there are points on the boundary of T that happen to be in the interior of R. There are all these points speckled right over here. So you have to count those, and the number of those is the number of boundary points in T, but avoiding these three corners. So it's the number of boundary points in T minus 3. So now we have a relationship between area, boundary points, and interior points of all these shapes. You notice I've written these so that all of the same shapes lie sort of in the same columns. So if you label these equations 1, 2, and 3, what we'll do is manipulate these so that we get a lot of cancellation. Right? So the way to do that is if you see we have AR, if we subtracted IR and then subtracted BR over 2, we'd get a constant. It would be -1. So that would be nice to write down here. So we'll take then, like we said, take 1, subtract 3, and subtract a half of 2 and see what we get. So if we go to the first piece of this, we've designed this so that this quantity is -1 by Pix theorem. So we get a -1 over here. And if we systematically do the same thing with each of these right triangles, since they also satisfy Pix theorem, we get -1s as well. So the only thing left is really the contributions in each of these terms with the t. We get a sub t here for this one, equation 1. Then we get minus equation 3, so we have minus it minus bt plus 3. And then we get minus half of this, which is plus bt over 2. Okay, so this positive 3 and these 3 negatives go away. We have at on this side right over here. We get a -1. And then now we have negative it, which becomes an it over here. And then we have this total, which is negative bt over 2, which we rearrange over here to get positive bt over 2. And now we have Pix theorem for this arbitrary triangle. Really, really cool idea. So the idea again is we start with these shapes with a rectangle, then we can use that to get the right angle triangle. Now we decompose this to get a arbitrary triangle. So let's do one more decomposition like this, where we take an arbitrary shape and then ask, how do we figure out Pix theorem for that arbitrary shape? So now the question that remains for us is, how do we deal with Pix theorem for a general polygon like this? So the ideas we had before are anytime we have a shape that we know Pix theorem for, we can use that to make some type of dissection in order to find out Pix theorem for other shapes. And here what we can do is actually split a polygon into triangles. So there are lots of ways to do this. Here's one way to do it with this actual triangle. Oh, I'm missing one other line segment, another line segment. Okay, so if we do that, we can sort of piece together Pix theorem on all these triangles to get Pix theorem on the entire polygon, hopefully. Now, it'd be tedious to do this with a whole bunch of triangles all at once. So what we can do instead is think about this as an inductive process where we do something like we have our polygon, we split it into a smaller polygon Q and a triangle T, hope that Pix theorem works here. It does work here because this is an arbitrary triangle, and then we perform the same procedure on this. We split it into T and Q prime, hope is true here, continue by adding this triangle T prime, etc. Now this process can be done by inducting. Instead of doing this like iteratively downward, we can induct on the number of triangles in a triangulation, so that we just have to do one step. So here we're going to say induct on the number of triangles in a triangulation of your given polygon. Let's say you had a polygon P that looks something like this. And let's say P splits up into n triangles in a triangulation. We'll cut off one of these last triangles right over here, call it T. Right, and then the remainder thing is a polygon called Q. And since we're inducting on the number of triangles in a triangulation, Q, by triangulating P the same way we did originally, that'll give us a triangulation of Q with fewer triangles. So by induction, Pix theorem is going to hold on Q. So let's write down Pix theorem for both Q and T. So now, what we want to do, like we did previously, is relate the area of P, boundary points of P, interior of P, somehow to Q and T. So first, we know that the area of P is the area of Q plus the area of T, because we've dissected P into T and Q themselves. So now let's look at interior points of P. The interior points of P are the interior points of Q together with the interior points of T, but there are these points in here that need to be added. So let's give a name to these points. Well, maybe label the number of points there are. Let's say there are X points over here. We don't know what that is, but we know that the interior points of P then is going to be the interior points of Q plus the number of interior points of T plus whatever this value X is that we don't know. Okay, now hopefully somehow this X will come up into boundary points, but we'll see. So the boundary points of P are all these points here. Let's relate them to the boundary points of Q and T. So the boundary points of Q is everything over here. So we get boundary points of P, but we also get these additional X points. So that is an extra contribution. Then the boundary points of T, we get these remaining points in the boundary points of Q, but we also get another contribution of these X points, and we've double counted these two. So the contribution from the boundary points of Q are the boundary points of Q itself, but we need to subtract this X. And then the same thing with T, we need to subtract X as well. But then even if we do that, we get this double count, so we need to subtract 2. Okay, so if you clean that up, that's BQ plus BT minus 2X minus 2. So now if we want to figure out what's going on with these three quantities, we hope that A minus I minus B over 2 is -1, so let's check that actual quantity. 1 minus 2 minus a half of 3 is equal to, because of Pix theorem on Q, we get a -1 here. Because of Pix theorem on T, we get a -1 here. And then we get no contribution here, minus this X, and then minus a half of this quantity, which is plus X plus 1. Now this negative X and X cancel, this -1 and 1 cancel, and we're left with -1, which is exactly what we wanted this quantity to be to get that P satisfies Pix theorem as well.